Welcome to the 10th lecture on approximation algorithms. Today we will learn about a polynomial time approximation scheme for the Euclidean traveling salesman problem that was developed by Sanjeev Arora in 2010. Let's start with the problem definition. So the question is, imagine you're a postman and you've got several parcels in your truck that you have to deliver to some houses. And the question is, what's the fastest way to do that? Go to all the houses and then go back to your facility. Or you can take the classic example that you're a traveling salesman and you want to visit all cities, or that you're Santa Claus and you want to bring presents to all the houses. So we are given a set of n houses, which are just points in the plane, and we want to find a tour between them. That is also called a Hamiltonian cycle. And the tour visits every house exactly once. Of course, we don't want to find any tour, but we want to find the fastest. So under all Hamiltonian cycles, we want to find that of minimum length, which in this example would be this one. The thing is, this is a very hard problem. If you remember Cake Center, they are told you if you take any polynomial, then you cannot approximate the K-center problem within factor of this polynomial. Here it's even worse, because you cannot even approximate it with factor 2 to the polynomial. So whatever you pick, it can be n to the 100, there is no approximation algorithm that guarantees a factor of 2 to the n to the 100. Unless p equals mp, of course. So this is terrible, and in the K-center problem what we then did was, we said we only look at the metric case. So we restricted the edge lengths, which is here the distance between 2 points. And of course, we can also restrict this here to a metric case, that we have a triangle inequality between all edge lengths. If we do that, then there is a 3/2 approximation for this problem. And for a lower bound, we know that we cannot be better than factor 123/122. So there is at least some lower bound, and we cannot have an approximation scheme. We cannot get a 1 plus epsilon approximation for every epsilon. However, in this very specific case, where we just have points in the plane, we can also just assume that we can fly. That brings us back to the Santa Claus example. Of course, Santa Claus can fly between the houses, so he doesn't have to use metric edge weights, but he can use the Euclidean distance. He just can take the direct segment between any two houses he visits. And this is the version we want to look at today, where we have Euclidean distances, and then we can be even better than this 3/2 approximation. We use a few simplifying assumptions. The first one is that we have some square of side length L times L that contains all the houses. That of course we can do by just taking the instance and scaling everything down. That doesn't change anything, we just solve the scaled version and then scale it up, and we still have the same approximation factor. Then we also assume that the size of this square is exactly 4 times n squared. As I told you, we can pick this L however we want, so it's fine. Just pick 4n squared, scale everything, it's good. And we know that 4n squared can also be expressed as 2 to the k if we choose k to be exactly 2 plus 2 log n. We will use that k in the next part. And the third assumption, for that one you don't immediately see why we can do it, but we can also assume that all the coordinates we have here are integer. So we don't have a house somewhere here in the middle, but we can round all those to integer coordinates. And why we can do that you will have to prove in the homework assignment. And the key basically is that we pick the square of size 4n squared, so when we move a house a little bit, then it's only by a very small factor that depends on this L, and that doesn't change the solution too much. And since we want to find an approximation scheme, the goal we have is to find a 1 plus epsilon approximation for any given epsilon for this Euclidean TSP problem.